I'm Charles Parker, the VP of Machine Learning Algorithms here at BigML. And so we're going to talk about our new resource, Deepnets, and specifically we're going to talk about what makes the deep learning that we're trying to introduce here at BigML more interesting, easier to use, and different from the deep learning packages you might have seen out there that exist out there in the wild right now. So first of all, why do we need another supervised machine learning algorithm on the BigML platform? We already have decision trees, we already have random forests and bagged decision trees, which perform very well. We also have logistic regression, which is great in certain cases. We have boosted trees, which are also kind of state-of-the-art in general for classification performance. So we have all of these supervised learning models that basically solve the same problem, which is these classification or regression problems. Why do we need another one? And so the main reason we're bringing deep neural networks is, of course, performance, right? They've been shown to be state-of-the-art in a lot of these niche applications like computer vision, speech recognition applications, some natural language processing techniques like language generation and understanding, things like this. So the problem with deep neural networks, kind of as we see it, if you're a novice or someone with no special expertise in deep learning, these networks have been historically difficult for people to train and use. And so this sort of pinpoints the goal we're looking for when we designed our deep neural networks. The goal we were trying to achieve is sort of made obvious by that fact, that this difficulty that novices have in using these things. So first, just to mention briefly what BigML Deepnets are not, is these networks that solve these niche problems that I was talking about before. So we don't have support yet for convolutional networks because those sorts of networks are typically employed in computer vision and signal processing problems. We don't have support yet for recurrent networks because these are networks that are typically used in solving these label sequence problems. So we don't have these niche networks yet that are designed for specifically structured data. The reason we kind of put support for these off until later is because these solve a particular subproblem, right? If you're coming with a computer vision problem, you need something like AlexNet or ResNet 50, one of these convolutional neural networks. That's the sort of network topology and structure that's good at solving these computer vision problems, and similar for recurrent networks and these label sequence problems. If you're a DeepNet engineer and you can very carefully tweak these parameters and tweak the structure of the network, you can get very good performance on these very specific problems. And so what we wanted to do at BigML is sort of be that expert for you. So can we bring the power of deep neural networks to your problem, even if it doesn't have this specific structure that a lot of traditional deep neural network, the specific structure that a lot of problems that have been attacked by deep neural networks have. If your problem doesn't have that structure, if it's not a computer vision problem, if it's not a label sequence learning problem, can we still bring some of that power we get from Deepnets to your problem? And so to do this, to talk about how we do this and how we're going to go about this, let's try to separate some of the myths from the realities when we talk about deep neural networks. Myth number one. So if you've read the media about deep neural networks, if you've read kind of the news stories about it, of course, deep learning is this thing that's going to make computers super intelligent, and it's going to either lead us to paradise or the underworld, depending on your particular apocalypse proclivities. This is not the case. Deep neural networks are, again, just another machine learning algorithm, and they work in basically the same fashion as all other machine learning algorithms. And in fact, if you want to look at them in terms of, kind of the broader picture of machine learning algorithms, you can do that. So if we talk about some of the weaknesses of the existing classifiers on the BigML platform, maybe we can get a sense of where deep learning fits into kind of the spectrum of machine learning algorithms that are out there right now. So if we have trees, trees are very good. Why are trees very good? Because they have this massive representational power, right? If you bring more and more data to a decision tree learning algorithm, you have more and more opportunities to split on that data. So you can have more and more thresholds, and you can represent functions that are more and more complex. Your trees get bigger and bigger depending on how much data you bring to the platform. On the other hand, if you have a certain sort of objective that you're trying to learn, for example, an objective function, you're trying to predict a function that's strongly multivariate or that can't be represented easily with these axis-aligned splits that decision trees induce, then you're going to have problems, right? Decision trees are designed to learn these functions that are able to be composed from these splits creates during the learning algorithm. So if your function that you're looking for, the function that you're trying to model, the prediction that you're trying to make, can't be made as a sequence of these thresholds, then you're out of luck. And so we mitigate some of these difficulties by using ensembles, right? And when I say ensembles, I'm talking about the most general use of the term ensembles with regard to decision trees, where we create a bunch of bootstrap sets, subsamples of the data, and we learn a tree over each one, and then we vote the predictions. And so this voting process can mitigate a lot of the difficulties that trees often have. If you smooth out over a bunch of trees, it's easier to learn. If you use a bunch of trees, it mitigates the variance that trees usually have by splitting too much, by splitting on data points that don't necessarily justify a split. So that's nice. We have trees which are powerful but have some problems. We have ensembles that kind of mitigate the difficulties that those trees sometimes have. So we also have on the BigML platform logistic regression. The nice thing about logistic regression is if you've got a smooth multivariate function, you get fast optimization for that function. So if you're looking for a linear function of your inputs, we can find that very quickly using logistic regression. This was a problem with trees, right? Trees only look at one feature at a time, and they do these individual feature splits. Logistic regression doesn't do that. It takes kind of a more unified feature space and does gradient descent on the parameters inside that space. Of course, the con here is that you lose that representational power that trees have. Logistic regression, you're trying to fit a coefficient for each feature in your data, plus a bias term, maybe. But if your decision function, if the right decision function can't be expressed as a linear combination of the features in your data, then you're out of luck. Whereas with trees, bringing more data to the platform will help you. If you're not learning the right function, you bring more data to the platform, the representational space of trees expands with that data. Logistic regression, that's not the case. You bring more data to the platform, and logistic regression will just be more sure about the same wrong answer it's already giving you. So is there anything we can do to mitigate that problem with logistic regression? So this is one way we can look at deep nets, is sort of a mitigation of these problems that algorithms like logistic regression have. And so with logistic regression, if we want to represent the logistic regression algorithm in terms of circles and arrows, which we always want to do in computer science, we love circles and arrows, we're going to do it like this. We have at the top here, these three circles represent one circle for each output class here. So each one of these represents the value for a possible output. Here we have a problem with 3 classes. And our inputs down here, each one of these circles represents an input feature. And as you can see, the outputs are a function of all of the inputs. Each output is a function of all of the inputs. And what sort of function? Well, the main thing is we're going to assign a weight to each of these inputs. So we're going to learn a number for each of these arrows. And then we're going to multiply that weight by the value of the feature, and then apply the logistic function to get a nice probability for class A in that case. And we're going to do that for each node and for each feature, and then we'll get a series of weights for all the features for each class, and that will be the mathematics that generates the predictions. So that's good, right? But we talked about how logistic regression, if it can't express the probability of a given class using these weights and the input features and the bias term, if the hypothesis, if the correct function is not in that space, then you're out of luck. So what can we do? Well, one thing we can do is maybe add a bunch of intermediate nodes here. So you see in this middle layer of nodes, you're doing the same thing as you would normally do at the outputs. You're learning a bunch of weights, one for each arrow, and you're multiplying the input features by those weights. And then you're applying some function on top of that multiplication, the activation function of a neural network, to normalize that dot product in some way. So it's basically the same thing. You've got a bunch of input features, you're learning these weights, you apply some function, and then you pass that function on to the next layer up. So now the probabilities are not a direct linear function of the inputs. The probabilities are kind of separated by the hidden layer from the inputs directly. And it turns out this massively increases the representational power of, say, logistic regression, because you've got all these extra nodes. So now you've got all these extra parameters. More parameters generally means you have a bigger space of classifiers that you're learning in. And in fact, it turns out, if you look at the theoretical machine learning literature, basically proves that given enough of these arrows and enough of these nodes, you can represent any function that you want if you have infinite training data. So we always like to see those bounds in the machine learning academic world, where if you get enough training data, you can represent the thing that you want. So now looking at this picture, you should be thinking to yourself, oh, the possibilities here are endless, right? Not only could you introduce a hidden layer with 5 nodes, but if you wanted to, you could also just add as many nodes as you wanted in the middle there, right? There's no reason to stop at 5. You could add as many as you wanted. And like I said, more arrows gives you more representational power, so you might want to do that. Similarly, you could add more than 1 layer, right? There's no reason to stop at 1 here. The only thing that limits us here is our ability to differentiate the objective that's induced by this network. And adding hidden layers does not impact that ability at all. We can still do learning on the network if we add hidden layers. Similarly, we can change these activation functions, right? I said we were using the logistic function here to normalize the dot product of the inputs with the weights, but there's no reason to use the logistic function. Again, we can use any function that's differentiable here, any function that we can learn the network with. So those could change too. And so there's a whole bunch of possible parameters here for this network. And one of the things I'd like you to take away from this presentation here is that deep learning isn't just a single algorithm in the same way that sort of decision trees or logistic regression are kind of a single algorithm. What we're talking about when we talk about deep learning is kind of a large family of algorithms, because the structures you can construct to learn over are kind of limitless. And in fact, if you look at the things that people use to solve these niche problems, the vision networks, the convolutional networks, and the recurrent networks, they're all basically variations on this theme, right? You've got some computations, you're passing those computations into nodes, you're applying functions on top of them, and then finally you're using gradient descent to learn all of the parameters that your network structure induces. Okay, so that seems awesome, right? Now we have a way of constructing a whole bunch of different network topologies. We kind of understand that we can do that regardless of the data that we get in. We can kind of make these arbitrarily complex networks. And so that leads to myth number 2, which is that deep neural networks are great for these marquee applications, for these applications where you have an expert constructing a particular network structure that does well for this problem, but they're less interesting for general use. There's no possible way that we could learn effectively over this massive space of networks and get something that's right regardless of the data that you bring in. We're going to try to drag that idea from a myth or a reality back into a myth. We don't think that this is true. And part of the reason that people think this in general is because there's this paralysis around all of the parameters that you could possibly have. You're choosing a gradient descent algorithm, which has a lot of options. As I said before, you have what number of hidden layers that you're choosing and what activation function do you want to use in each layer or for each node even. How many nodes per layer do you want? And then there's the sort of the gradient descent parameters like the learning rate, and do you want to use dropout training to prevent overfitting? How big of a batch size do you want to use if you're doing gradient descent in mini batches? It just goes on. And then there's like the things that are kind of fancy and new to the deep learning world, like batch normalization and residual networks. And that's not even taking into consideration the usual machine learning algorithm parameters like missing numerics and objective weights, things that apply to all machine learning algorithms. And we're not even getting into the algorithms that are specific to each descent algorithm up here. So this is crazy, right? There's a ton of parameters. Let's even take a look and see what this looks like in the BigML interface. So if we look here, we'll talk a little bit more about this DeepNet training set in a bit. But if we go down here to our configuration panel and we go to configure a deep neural network, okay, there's a few parameters up here. You know, that's not so bad. But you open up advanced configuration and network architecture. Oh my God, you can have a bunch of different things here. We can add arbitrary numbers of hidden layers. If I turn off automatic optimization here, we can have an arbitrary number of hidden layers here. So a ton of these, each one of these has an activation function and a number of nodes. And you can kind of add a whole bunch there if you want. You have all the binary parameters. And then down on the descent algorithm, as I was saying, there's a bunch of parameters that are specific to the descent algorithm. This is a lot of work, right, to specify one of these networks. That's why we pay experts a ton of money to solve these niche problems that are very valuable to solve. I want to stress here that this configuration panel with all these options here, it's not like learning decision trees or ensembles of trees where they're pretty much invariant, or they're not invariant, but they're less sensitive to the parameters that you specify. If you learn too many trees in an ensemble, that's really no big deal. A 100 tree ensemble and a 200 tree ensemble, as long as you've got enough to mitigate the variance of the underlying trees, it's not a big deal. You're not going to get much of a change in performance. Whereas if I say mess with this learning rate here, anybody who's learned deep neural networks knows that if you have this learning rate, you know, off by even an order of magnitude, you can get very different results, much worse than you would if it was in the right zone. So a lot of these parameters are incredibly sensitive. You move them just a little bit and you get a network that's totally useless, and you move it a little bit the other way and you get state-of-the-art performance. And so what can we do about this? This is kind of a big problem, right? Clearly there's too many parameters here to fuss with manually, unless, again, the problem you're solving is something that Google needs to solve, like this vision problem. We don't want to have to build, if we have data that doesn't fit into one of these niches that deep networks are already used for, we don't want to have to manually build a network. We don't want to have to manually choose all of those parameters. Why? Because setting them takes significant expert knowledge. Either you have to A, know all about these things and know how to set all the parameters and how to construct a good network for your problem, or B, you have to play with them until you get something right. Both of these are kind of tedious and unlikely. And so we're going to deal with this in two ways on the BigML platform. First, we're going to do meta learning, which will give us a good initial guess as to what a set of parameters are that will work for your network. And then second of all is we're going to do network search. So if our initial guess doesn't give you a great deep network the very first time you try, we have functionality that will try a whole bunch of networks and measure their performance and return you a good network based on that search. So first of all, meta learning. Let's talk a little bit about how we did that. We trained almost 300,000 deep neural networks, so you don't have to. If you really enjoy training deep neural networks, you can train 296,748 networks. It was fun, I did it. But if you want the benefit without having to wait, a good month of machine time to get the results, you can just use BigML and you can get all of that knowledge. And what do we mean by all of that knowledge? Well, let's look at what the data set generated from these 300,000 networks looks like. So basically what we've done is we've trained 300,000 networks on 50 different data sets on various folds of cross-validation. We've taken the structure of the network and the parameters related to the data. We've made that into a data set. So here you see this data set. You see that it's got exactly as many networks as I said, and the data set itself has various parameters about the network. Each instance has parameters about the network itself. So whether or not it was a residual network, the activation function we used, dropout rate, and so on and so forth, a bunch of parameters that we're modeling that have to do with the network. And then we also have features about the data on which the network is trained. So how many instances were in this data set, how many features, the number of classes, the percent of the class, the percent of the data set that was the minority class label. And then at the end is the rank percentile. So basically for this data set, for this fold, for this cross-validation fold of this data set, we trained 128 networks on each fold of cross-validation for each data set, and then we measured the relative performance of those 128 networks. And so some of these network structures, given the data that they're trained on, are not going to work very well. And it's possible that the same network structure trained on a different data set works quite well indeed. The idea here is that you choose your data set, you choose your network structure, and you get some relative performance. There's some networks that are the best for that data, and there's some networks that are the worst, and we're going to measure where they occur in the spectrum, with the very best being the ones that have the highest rank percentile here. So we've got this data set that could possibly tell us a lot about which neural network parameters work for which data, and we're just going to create a machine learning model, right? Why not use machine learning to extract all this information? And so we've done that, and it's right here. And so just to give you an example of the information that's contained in this model, let's look at the learning rate versus the batch size that the network is being trained on this plot. So on the y-axis here is the mini batch size for gradient descent. On the x-axis here is the log of the learning rate we're using to train a network. And you can see that for the Atom descent algorithm, where we've used rectified linear units for all of our activation functions, for the activation functions for every node in the network, you can see that there's some zone where you want to set your learning rate, which is in green here. That's where you get the networks that are the best relative to all other networks. And if you set your learning rate incorrectly, you go into the blue here, which is networks that are not as good. So that's some information, right? And you can also see that we're kind of invariant to the batch size. We need to use batches on average bigger than about 40 to train the neural network, but anything beyond that is kind of gravy. You can use any batch size you want beyond about that number, 40 or 50 here, and be relatively sure you'll get the best network that you can get. So that's pretty nice. Let me see if this works here. So now let's change our descent algorithm. Let's say instead of using Atom, let's use Momentum. And you can see, wow, that's quite different, right? Momentum expects a learning rate to get the best network out of the Momentum algorithm. It expects a learning rate several orders of magnitude higher than the one you should use with Atom to get the best expected network. Again, this is log scale down here. So this is, we're using 10 or 100 times the learning rate that we did with Atom to get the best performance out of the Momentum descent algorithm. So yeah, that's interesting, but maybe Momentum is just kind of an outlier here. Maybe maybe all the other descent algorithms prefer a learning rate that's somewhere in the middle, just like Adam did. Let's try another one here. Oh, of course, I've got this example set up ahead of time. RMS prop requires exactly the opposite changes to the learning rate to get the best performance, right? Now we're using learning rates that are a 10th or a 100th of what we were for the Adam learning algorithm. So this is the sort of information that's contained in this model of network performance, is that you've got these different descent algorithms and you've got learning rates, and you need to choose a different learning rate depending on the descent algorithm that you're using to get the best expected performance. And it's not just that, right? There's a whole bunch of parameters here, again, that we can fuss with that might change the performance of the network. And all of that information is kind of contained in the model. The wisdom of those 300,000 networks that we trained are contained in that model. And so what do we do at BigML? When you want to train a new network, the one-click option that you get, let's see if I can go back here. So if you create a one-click DeepNet, that's exactly what it does. As it goes, it looks at your data set, it looks at all the possible parameters you could have for that neural network, and it chooses a good set of parameters based on the data set that it sees. And this all happens behind the scenes. You just get back a regular model like you would with any other modeling technique, but the model that you get is tuned to your specific data. And if you do happen to be in the configuration panel here, the automatic optimization button, as long as this is suggested, or as long as this is selected, it'll do that structure suggestion for you. It'll look at your data and it'll try to find the best structure it can based on that model. So that's pretty nice. We've trained all these 300,000 networks. We have a nice basis for which to choose network structures on. We're not just going to leave you hanging there and have you set all those parameters yourself. And we're not even just going to pick default values for you. We're going to look at your data and we're going to try to find the best network we can based on that data set that you come with. We're not just going to give a generic suggestion. We're going to personalize it a little bit for you. So that's pretty good. We can make a good initial guess, but it might be wrong, right? It's an educated guess. It's made on the basis of those 300,000 networks that we trained, but it might be wrong. Again, we quote unquote, only looked at 50 data sets when we were making these 300,000 networks. So it could be that you come with a data set that's very different to all those 50 data sets that we looked at. There's nothing really even that close to your data set. So what happens in that case? What if we suggest a network and you get it back and it's just awful? And that happens. That's even happened to us when we're playing with the platform to the staff at BigML. Every once in a while, you'll train a network that works well for a lot of other data sets. And so we suggest you that network and it turns out to be terrible. So what happens in that case? So this is why we offer network search. With network search, we're going to try a whole bunch of structures like you see on the left. So we're going to use our initial guess and maybe the second and third and fourth best guesses to populate this set of structures that we're going to try on your data set. And then we're imagining in this box here, model and evaluate, that we're going to construct the network and we're going to measure its performance, right? We're going to use some held out chunk of your data, or we're going to do cross-validation, or there's a number of ways you could do this, but we're going to try the network, we're going to train the network on part of your data, and we're going to evaluate it on part of your data and see how it does. And so if we do that, we train on our first structure, we get 0.75. Again, there's many ways of measuring performance, but this is the flavor of the algorithm. We get 0.75, whatever that is. And so we decide, that's okay. Let's train on the next structure that we're guessing will work well. Oh, look at that, 0.48. That didn't work so well. That's too bad. We tried one and it didn't work out. Let's try the next one. Hey, look at that. The next structure it gives us better performance than the first one did. So that was unexpected. We tried the first one. We expected that one to be the best, and the one that was third down the list ended up being the best. Who knew, right? So now we have all of this information about how networks perform on your particular data set, right? The initial suggestion we made was based on a bunch of different data sets, was based on our repository of interesting data sets. But now we have your data set and we're looking at it, so we can make a better guess, can't we? As we try 3 or 4 of these possible networks, some perform well and some don't. So why not use machine learning again to help us out with this choice? So here we're going to use machine learning on the networks that we've already tried, and we're going to let that. You can see if I go back a slide, here we have some ordering based on our initial model of what good structures look like, the one I showed you before. And now we've trained a model on your particular data based on the structures we've tried so far. And so we might reorder those. We might say, oh, look, this tends to work well on this particular customer's data set. Let's try this structure that looks similar to that one that worked well first, before we try these other structures that don't look like they're going to work out as well. So again, there's another level of machine learning that's happening on top of this network learning, is that now we're learning which structures work on your particular data set. This is something that happens behind the scenes. It's totally transparent to you. That's what we wanted to invent here, was something that was mostly transparent to you. If we go back here, we see that all of that logic is contained in this button here, the automatic network search. So if the suggested structure doesn't work out well for you, we'll do the search. The reason not to do the search right away is because it takes a lot more time. If you can imagine the structure suggestion, we suggest the structure, we train it, then we give it to you, and we're done. With the network search, we're going to train one, and then we're going to train another and another and another, and then we're going to construct a model of how well those work, and then we're going to train another and another. So network structure search tends to take quite a bit longer than the structure suggestion. Orders of magnitude, like 10 times longer or something like that. Thankfully, here we have this max training time. So basically, it's an anytime algorithm. A half hour is good. It's enough to learn. Yeah, it's enough to do a good search on most data sets, a half hour. If you have a particularly large data set or a particularly wide data set with a lot of features, you might want to increase this number. And if you're feeling very impatient, you might want to decrease this number. But in general, the longer you give the algorithm to search, of course, the better a solution it will come up with. We've constructed this thing that we hope is very hands-off, and we hope will give you a really good network without you having to do much work. All you have to do is click search and you're done. And so let's benchmark, right? Let's look at the performance of these networks that we get out. And of course, we don't want to do this lightly. I've seen too many crummy benchmarks, and in fact, a lot of my academic papers are on this topic of benchmarking. The ML world, both in the academic world and in the industry world, it's just filled with benchmarks that are inadequate. People don't use enough data on their benchmarks. They take one data set and they do one little holdout set, and then they try a bunch of algorithms on that data and that one holdout set. And they declare victory or defeat based on whether or not it performed well on that one data set, on that one holdout set. That's sloppy. You need to try on multiple data sets, and you need to do cross-validation to get a general idea of how well an algorithm is performing. Also, one metric. So if you're in industry and you happen to know exactly the function you're trying to optimize, absolutely use that metric. But if you don't, if you're using some proxy like accuracy or area under the curve, or the phi coefficient, or any number of other things that you could try, don't rely on just that one metric unless it matches exactly the performance you need in the real world. Use a bunch of metrics, right? There's a lot of different ways of measuring classifier quality, and you're not going to get a general way unless you use a bunch of metrics. So the solution here was to roll our own benchmarking. And so again, we have these 50 data sets, so it's easy to do this benchmarking. And before you ask, no, we didn't use the structure search model to inform our deep nets here. That would be cheating. We use those 50 data sets and we use the software before putting in the structure suggestion model. So really all that's happening here is the individual modeling on each data set as we go through the search. So there's no contamination of this benchmark, because that would be cheating, and we don't want to do that. So we've got 50 data sets. We do 5 replications of 10-fold cross-validation on each one, and we're measuring the quality using 10 different metrics. And we're going to measure, our competition is going to be 30 competing algorithms. This is actually a project I started before I came to BigML. So I went looking for all the possible machine learning algorithms because I was interested in kind of in general, what's the very best algorithm? Does it kind of match the folk wisdom we quote unquote know from the machine learning academic literature? And so I looked at all of a bunch of the algorithms in R, a bunch of the algorithms in Scikit, Weka. I used XGBoost because that's known to be a good performing algorithm. And in every case, I'm just pulling this off the shelf and putting the data into it. I'm not doing a lot of elaborate parameter tuning or anything like this. I'm interested in off-the-shelf solutions because, again, that's what we're trying to design at BigML, is something that you don't have to fuss with at all, something where you just put in the data and go. And again, because I started this project before I came to BigML, it's on my personal site, so it's this is the web address. And let's just take a look at it. I wouldn't be showing it to you unless we won, and we do in fact win. So you see that doing these parameter optimized neural networks does in fact give us a big boost over everything on this metric. And what's everything here? So in this case, when I talk about a boost, what I'm measuring here is value captured. And the way I'm defining value captured is how much of the performance that you could get on this data set does this algorithm capture. So if the best over all of these 30 plus algorithms, if the best accuracy you could get was 75%, we're going to say that's the best you could get. And anybody who scores 75% gets a 1 here. And so and I do that for every metric on every data set and then average the results. And so you can see deep neural networks is capturing 83% of the value you could possibly get, which is quite a bit better than the next best contender, XGBoost at 75%. And this is kind of a nice plot because it does sort of confirm what we know about machine learning in general. You see the gradient boosting algorithms, the random forest algorithms are up here at the top. Here's multi-layer perceptrons and scikit-learn, a kind of competing deep neural network package that doesn't do this parameter optimization. And so extremely randomized trees, these are algorithms that we know work very well at the top here. And of course, at the bottom are these things that we know aren't as good: individual decision trees, naive Bayes, and so on and so forth. So it confirms our intuition, and it also shows that doing these parameter optimizations, you can get really good performance out of deep neural networks in just one click with no particular hand tuning, with no particular expertise in deep learning. You can usually get something that will work very well on your data, regardless of what it is. And if you're curious about the 50 data sets we used for benchmarking, you can see they're all listed down here. And the domains, some are fake data sets, some are computer vision, text labeling, a wide variety of domains. I tried to cast as broad a net as I could when I was constructing this benchmark. So feel free to go here and take a look at the benchmark. It's a rather interesting thing to look at on its own. But again, the takeaway here isn't that, oh, deep neural networks on BigML are the best thing there is. That's not true, right? If you were willing to try all of these things, if you yourself wrote some code that tried all of these algorithms in R and in scikit and in Weka, because I did that, and it takes a long time to get that right. But if you did that and you picked the best one out of all those things, you could probably get performance that exceeds what I'm reporting here, right? If you're willing to do some meta learning, you could probably find ways to improve this performance. But there's nobody yet, there's no package yet that I could find that's as easy to use as just picking up scikit and plowing data into it, or picking up BigML and plowing data into it. So when somebody makes that sort of learning one click easy, I'll be able to do an appropriate benchmark against BigML, where I'm parameter optimizing, in ways that other people do. But for now, you can see that this algorithm is giving you the best thing that you can expect most of the time, without having to do any futzing. And so that's a pretty good deal. So the reason that we're able to do well here is because we have the patience to search through all these possible structures, right? It comes with a cost, and mainly the cost is that if I go over to training time here, I sort all of our algorithms by training time. BigML, the deep networks in BigML are quite a bit slower than even the next slowest thing, which is the deep neural network software in Weka. And this is a log scale on the side here, so these are orders of magnitude. So it's 1 or 2 orders of magnitude slower than training a single network in scikit. So that's a downside, right? You have to be willing to wait for that good performance. You have to be willing to sit there and let the algorithm do its thing and search to find a good network for your problem. Again, there are a lot of networks out there. The space is huge, and a lot of them don't work very well. So it takes time to find one that works for your problem. And so that speaks to this myth. Oh, deep neural networks are great as long as you're willing to spend the time. We can get really good performance. Or if you know how to do really good hand engineering, we can get really good performance. And so we can throw all these other machine learning techniques out the window, all the other supervised techniques, and we can just use deep networks for anything. No, don't do that. Geez, hold on, just settle down for a second. There's a few kind of buyer beware sort of qualifications we want to offer. So I've kind of been stoking the fire for this whole little presentation here, and here I'm going to pour water on it. Things that make deep learning less useful. First of all, if you have small data, and small data in your case could even be thousands of instances, the deep neural network learning algorithm relies on lots of data to fit those very complex structures. So if you don't have a lot of data, the structures that could possibly work, it's a much smaller number of them. And so even a search might not find a thing that's very good for your data. So again, you have to kind of obey what I call, if you sign up for our advanced machine learning training, you'll hear me talk about the triple trade-off in machine learning, which is the trade-off between how much data you have, the complexity of the hypothesis space, or the complexity of the classifier you're looking to fit, and the amount of error that you're looking for. So if you don't have much data, either you have to use a simple classifier or be willing to put up with more error. And that law still applies here, the same as it does to all other classifiers, is that if you have small data, you just can't fit things that are very complex. And so you're not going to do as well as you would if you had more. The next thing here, problems where you could benefit by iterating more quickly. So a lot of times, if you can, hand engineer features that are really nice, or you can go out into the field, quote unquote, and get more data, that will help your model's performance a lot more than getting fancier with modeling techniques. So if you could better spend the time it takes to train a whole bunch of neural networks by just training a tree and seeing how well it does, and training a tree and seeing how well it does, if you could use that time to iterate better, to go off and get more features or hand engineer things, then that's probably the way you should spend your time. You shouldn't just sit in front of your computer twiddling your thumbs, waiting for the computer to do something good with deep neural networks. If you can hand engineer features that are better, you should just do that rather than paying the extra cost in terms of training time. And then finally, problems that are easy, or for which top of the line performance isn't absolutely critical. If your problem is easy, if a tree solves it as well as it can be solved, there's no good reason to use neural networks. Trees are a lot faster to fit, and they're more interpretable, right? You can just look at the set of rules, and you can see exactly what the tree is doing. We're trying to bring a capability like this to deep neural networks, and we probably will in the future. But for now, trees are the most interpretable algorithm that's out there. You just look at the structure of the tree, and you can see exactly what it's doing. So if you can use a tree, if it performs very well for you, then go ahead and use it. And there may be other things. Again, the speed of the classifier in situ, right? If you're in a production setting where you can't wait a few milliseconds for the prediction, you might want to use a single tree because it's blazing fast. So there's a lot of reasons to use a simpler classifier. And just to show you that this is a little more than a myth, I'm going to go here to this Generate Abstract tab on my benchmarking site. And you can see I have all of the data sets plotted against all of the algorithms, where a darker square means the algorithm is better. And so what you'd expect if the ordering of the algorithms performance-wise was kind of invariant to the data set, you'd expect this chart to just be filled with vertical stripes given the performance of the data set. And you see that it is somewhat stripy, right? Algorithms that perform good in general have these big vertical stripes. So here's the deep neural networks in BigML. You can see it's fairly dark all the way down. However, if you take a particular data set here, like the mushroom data set, for example, and you slide over to decision trees in Weka, you'll see that the value captured is 100%. The Weka decision tree on the mushroom data set does as good as anything else, no matter how you measure it. Right, that's not a surprising result, because it's really easy to get perfect classification on the mushroom data set. If you know about the mushroom data set, we're talking about a data set that measures whether or not a mushroom is poisonous based on the kind of appearance and the smell of the mushroom and whether or not it has certain features. But if you know those things, you can figure out whether a mushroom is poisonous or not with absolutely no trouble. So decision trees perform as good as anything can. So why wouldn't you use them in this case? There's no advantage to using these fancier models if decision trees perform as well as you can. And in fact, if you just look up here at the top of this benchmarking site, you see that I've written a little function that'll auto-generate a abstract for you that tells you that a given algorithm is the best no matter what algorithm you choose. So for any algorithm, you can find data sets where it's the absolute best thing. And here I'm telling you that decision trees beat support vector machines in R and gradient boosting in R on 9 data sets. So that's crazy, right? Like decision trees are not better than gradient boosting or support vector machines. But if you're willing to choose the right data set and the right metric, you can always find something that's better than other things. So that's the last point of this buyer beware here, is that if your problem is easy, if you have some external factor, some data specific, domain specific factor that suggests that you should be using a simpler model, you should use it. The only reason really to use deep neural networks is that they perform better in some cases. So if you're not in a domain where they perform better, and you might be, then absolutely don't use them. Don't pay the cost of training them that can take a lot longer than these other classifiers. So in short, remember that deep learning, it's not magic. It performs well in a lot of cases, and at BigML we've gone as far as we possibly can to kind of making it easy for you to find a deep neural network that works on your problem. But it is finally just supervised learning. There's nothing super fancy about it. It obeys all the same laws as other supervised learning techniques. And it's worth quoting Stuart Russell at length here, where he says deep learning, it's been in the community for a number of years. The only reason it's really gained in popularity lately is because we have bigger data sets like at Google, where they have tons of data and they need to solve this tough problem, and they have really smart engineers. And so, minor improvements in the algorithm, specific engineering, loads of compute power, and huge data are the only reason these things have become popular. Other than that, they're really just not any different from any other supervised learning algorithm. If you're thirsty for more, after all of that deep neural network information, you can read our series of blog posts here, especially the dashboard documentation. Like I said, there are loads and loads of options for all of the various things you can do with our deep neural networks. So absolutely go through those. Do keep in mind that this is sort of a first iteration. As I said, those kind of specific niche problems where deep learning does very well, convolutional networks, recurrent networks, we're looking at adding those things in the future, as well as things that can make kind of general performance better on more general problems. So do keep an eye on our blog, on our documentation. As we add things, we'll make people aware.